everybody. My name is Mairead. I'm not going to reintroduce myself because y'all just heard that. I'm going to talk about where elements are made. It's what I spend a lot of my time thinking about. So I figured let's make a whole room full of people think about it too. So chemical elements are one of the smallest things that we sort of encounter or think about on an everyday basis. They're the building blocks of all molecules. So that's things like water, DNA, sugar, and we sort of encounter them individually as well, right? So the air that we breathe and the iron in our red blood cells that carries that oxygen around, those are elements. Mercury in thermometers, lead and copper in pipes, well, maybe not lead, gold in rings, lithium and nickel in batteries, neon, uranium, all of these are chemical elements. Even the iodine in our salt is a chemical element, and they all have cosmic origins. So we usually see elements arranged like this on a periodic table. This is the chemists doing all of these colors. They tell us sort of what elements are like each other that have similar properties, but that doesn't really tell us anything about where they come from or how they're made. And so we are going to recolor this periodic table tonight in a way that tells us something about the origin of each of these different chemical elements. So I'll start with a little bit of background, and then we'll just get going. We'll start talking about where all the elements are made more or less in order, the processes that make them, and then we'll end talking about how we know any of this at all, which is related to what I work on every day. So elements are particles made up of smaller particles called protons, neutrons, and electrons. And when we have protons and neutrons bound together, that's a nucleus. When we consider the electrons that are sort of orbiting our nucleus, that's when we have an atom. And for our purposes, the nucleus is the key player. Here we go. So when the difference between all of the chemical elements, all of which are atoms, is just the number of protons in the nucleus. So helium is the lightest element. It has just one proton. Hydrogen is the lightest element, has one proton. Helium has two. Iron has like 26, and so on. We can go all the way up past 100 protons. Now, the number of neutrons that a nucleus has determines which isotope it is. So all of these little toy nuclei here are helium because they have two protons, and they all have a different number of neutrons, so they're different isotopes. And so our trip is going to take us all the way through the periodic table to 118 elements, 118 protons. And we're going to start with hydrogen and helium as our building blocks. So they are the lightest elements in the universe, and they are primordial, meaning they're made during the Big Bang. So in the first couple of minutes of the universe, well, for longer than that, but in the first couple of minutes, we didn't have any structure. We didn't have any stars, no galaxies, no planets, nothing. We had one big, hot cosmic soup. And that soup sort of congeals into protons, neutrons, and electrons, and congeals further into different isotopes of hydrogen with one neutron or two, and also into helium. A tiny bit of lithium will be made this way, but almost none. And so we're really starting from just hydrogen and helium. When we look at the composition of the universe, almost all of it is at least all of the universe that we can see is in hydrogen and helium. Because we get them basically for free during the Big Bang. Everything else we have to make ourselves. Well, somebody else. And that everything else is just a couple percent, but it's most of what we care about, right? It's the carbon that makes us up. It's what makes our world. And so we need a way to get from this mess of hydrogen and helium that we have to stuff like carbon and oxygen. But we have to be a little bit careful when we do this, because not all nuclei are stable. We can't just start combining protons and stacking them all together and expecting to have a stable nucleus at the end of the day. So most of them are going to be radioactive, meaning they will have to rearrange themselves, gain and add other particles in order to sort of survive forever. And what this plot is showing you is the number of neutrons on this horizontal x-axis here, and the number of protons that a nucleus has on the vertical. And the gray line shows you where a nucleus has an equal number of neutrons and protons. And you can see this blue, thin strip of blue in the middle. That's where elements are stable. That's it. Everything in green is not going to survive very long. Everything in white can't even be made, much less survive under any circumstances, as far as we understand. And we can think about the stability of our nuclei sort of as a juggling act, where our protons are the jugglers and the neutrons are the pins that they're juggling. And if we were to have, if we were to give one juggler like 50 pins, it's not going to work very well. I don't know, I don't juggle, but I assume this is not tenable. And so what's going to happen is that our juggler is going to drop pins, or maybe they're going to pick up a friend so that they can handle the number of pins that they have. And so always these nuclei are going to tend towards this blue strip. And the heavier elements do the same thing. So if we have a ton of protons, a ton of jugglers, this is like now our Cirque du Soleil team, where one neutron per proton is not enough. You're going to quit the team if there are not enough pins to juggle. And so these heavier nuclei need to have more pins than jugglers, more neutrons than protons. And that's why you see this curve start to tip over like that. Now, there are a couple of exceptions to this. Some numbers of neutrons or numbers of protons in a nucleus are magically more stable than others. We say that if they have a magic number of neutrons or a magic number of protons, even if that ratio is really off, they'll survive not forever, but longer than we would expect. So if we have a nucleus that has 82 protons and not nearly enough neutrons, it'll last a little bit longer than something that had 81 protons in the same number of protons. And these magic numbers correspond to the elements like calcium, nickel, tin, lead, and to lots and lots of different isotopes, right? Lots and lots of different numbers of neutrons. Lots and lots of different elements with the same number of neutrons. These make things like platinum, stable isotopes of platinum or barium. And this is going to help us a lot later because nuclei tend to congregate around these magic numbers. And I'm not just calling them magic numbers, that is actually what they're called, because when one of the people who was working on it looked at like his co-researcher's work, he said it just seems like magic, and it stuck around, unfortunately. So what we need to do is not just change hydrogen and helium into heavier nuclei, but we need to make them stable enough for us to see them eventually, at least. Right? They have to survive from when they're made to when we can look at them today. So the next thing that we're going to do is start aging some nuclei and filling out our periodic table. And the first one that we're going to talk about is what makes the next lightest elements, which are the rest of the lithium, beryllium, and boron, which have 4 and 5 protons respectively. And they're made by fission, which is the splitting of a nucleus into multiple smaller nuclei. Fission is what is happening in nuclear reactors, and it happens in space too. So if a particle, like a neutron or a proton or an electron, gets accelerated to really high speeds, that can happen if it gets like spit out of the explosion of a star in supernova, or it can get sped up by a very active black hole at the center of a galaxy. And that particle is just going to go whizzing through the galaxy. Sometimes it's going to hit something. This happens all the time in our own atmosphere. And sometimes that whatever nucleus hits is going to split into something that coincidentally has 3, 4, or 5 protons. Now, this process doesn't have to make something that has 3, 4, or 5 protons, but there's no other way to make these elements by any of the other processes that we're going to talk about. So when we look at how much of the different elements there are, where top of the graph is a lot, bottom of the graph is a little, you'll notice that there's a huge dip right around lithium, beryllium, and boron. There's almost none of them, right? It's like 1,000,000 times more iron than beryllium in the solar system. And it's because the only way to make them is by this like very coincidental process. Okay, the more abundant elements on that plot are made by nuclear fusion, which is the combining of different nuclei to make heavier ones. And so you can imagine if we have our cloud of hydrogen, they're all moving around. Sometimes they will get close enough to interact with each other, and they're going to have to rearrange They're going to crash into each other. And what comes out of this reaction will be helium, random neutron, and some energy. But for this to happen, right, we once again need a very good coincidence. These nuclei have to pass each other by close enough to actually be able to interact. And that is surprisingly hard to do. The nuclei need to be at really, really high temperatures. There need to be a lot of them. They need to be very close together. So they need to be at like 10 million degrees Celsius. And that's because we want them to be moving very, very fast. They can pass by each other a lot. And they need, of course, there needs to be a lot of them, and they need to be pretty close together in order for this sort of reaction to happen with any regularity at all. And this is almost impossible to do on Earth, and it gets harder the heavier the element you want to fuse. But the good thing is, stars are just great at nuclear fusion. It's really what they do best. So they are a little chemical manufacturing plants, and during their life and during their death, often a supernova, they're going to produce really the rest of the elements that we're going to talk about. They're very effective. That's why you sometimes hear like the Carl Sagan quote, like, we're all made of star stuff. It's true. All of the stuff that makes us up was made in a star, but that is like really vague. Because lots of things are made in different places. So stars start off as clouds of hydrogen and helium. They'll usually have a little bit of something heavier mixed in that was left over from a previous generation of stars, but it's mostly hydrogen and helium. And gravity is going to start to draw that cloud of gas in towards the center. Right? Gravity always wants to attract everything towards one pole. And as that happens, the center of the star is going to get denser. It's going to heat up in this core. And eventually, as gravity keeps pushing in and keeps compressing this core, it's going to get hot enough, the nuclei are going to get close enough that they're going to start running into each other. We start to get hydrogen fusion. And this generates a lot of energy. And that energy is going to sort of push back against the force of gravity and support the star. It's going to stop it from collapsing. And eventually, the star will be sort of a balance between the force of gravity pressing in and the pressure from fusion pushing out. And it can stay here, burning hydrogen very stably, very calmly, for often billions of years. This is what our sun is doing right now. So once all of the hydrogen is turned into helium in the core of the star, nuclear fusion is going to turn off. What was hot enough for hydrogen is not hot enough for helium. And so nuclear fusion turns off. Gravity was there the whole time, but now there's nothing holding it back. And so the core is going to start to contract again. And once again, it's going to heat up. That's great. Eventually it gets hot enough to get fusion in the core. And so helium is going to be turned into carbon and a tiny bit of oxygen. And the carbon is made by what's called the triple alpha process. So helium is called sometimes an alpha particle for historical reasons. And to make carbon, we're going to combine 3 of them together. Thus the triple alpha process. And it's actually quite hard to do this, right? It was hard enough to get 2 things to collide. Now we have to do 3 at once. But stars can do it, and they will just burn their helium into carbon very stably once again for quite a long time. And almost all stars can do this. This is what our own sun will do. But once helium fusion is done, we're sort of left with the carbon-oxygen core. We have some layers of hydrogen and helium that didn't get quite hot enough to fuse. And from here, we can take one of 2 paths. Most stars are actually not massive enough to burn anything else in their core. No matter how much gravity tries to squish them down, they're never going to get hot enough to fuse that carbon into anything else. And so instead, they have some like weird intermediate life stages. It's going to like puff up. Eventually, it's going to expel this big cloud of hydrogen that's sticking around and leave just like a bare, sad little core left over in a beautiful planetary nebula. And that core is just going to, most of the time, it'll just hang out and cool off forever, not doing a lot of nuclear fusion. So for our purposes, that is not helpful. That has not made an element. It has certainly not made one that we can see. It all got trapped in this core. So instead, we need to look at more massive stars. So these are stars that are about 10 times the mass of the sun or more. So the mass of the sun is about 300,000 Earths. And so these are about 3 million Earths, up to maybe even 10 million Earths by mass. And these can absolutely get hot enough to start burning carbon into oxygen, and they can keep going for a while until their very untimely death as a supernova. So these massive stars fuse elements in their core by, once again, an alpha process. So it's called this because every single step of this chain is just going to be adding a helium over and over and over again. So the star at this point has mostly a core of carbon, again, teeny bit of oxygen, lots of helium knocking around still. And so one of those helium nuclei will just get stuck onto a carbon nucleus and they'll fuse. The star will keep doing this for a while. Once it runs out of carbon, it makes oxygen and produces energy. And once it runs out of carbon, it can start doing this to oxygen, just start tacking helium onto that. And then we can tack helium onto the neon that we've just made. And we can just keep going and going for a while anyways. This process has to stop at iron and nickel, no matter how massive the star is. And the reason for that is because iron and nickel are very, very stable. It is really hard to change an iron nucleus in any way. It's hard to take anything away. It's hard to add anything. It requires energy. And nickel is one of those magic numbers that we love so much. And so we can't just start putting helium on. Bummer, because now we have no fusion. Nothing is stopping gravity now. There is truly no hope for the star. So it's left with this core of iron ash and all of these other layers of the elements that it fused by this alpha process. And there's nothing to support it. And so the core starts to contract. And honestly, these are massive enough, they don't just contract, they completely collapse. The iron ash gets compressed into some impossibly dense core. And these outer layers are rocketing towards the core at up to like 25% the speed of light. When they hit the core, they're just gonna ricochet right off. And this is called a core collapse supernova. And we think this is something like what it might look like. So the energy involved in something like this is approximately equivalent to 2,500 billion years worth of energy from the sun. So there's a lot going on. There's certainly enough to fuse heavier elements than iron. Right? We needed an injection of energy in some way to get past this barrier, and now we have it by just completely destroying our star. So this ricochet off the core is going to produce a shock wave. And you can see that sort of propagate outwards. And as that shock wave expands and it's passing through these outer layers, which already had some heavier elements in them, right? These are layers that have neon and oxygen, silicon, things like that. It's going to take those and fuse them all together in very messy ways. And those outer layers escape, they get returned to the environment that the star was born in. Now, most of the iron that we made actually gets trapped. It does not escape, it got stuck in the core, never to be seen from again. But that's okay, because we can make some of these outer layers too. So that's not, that's not a big deal. And so these massive stars, by this process, can make elements up until about rubidium, ignore those three, up until about rubidium, which has 37 protons, which is great. We only have 81 more to go. And they make a lot of even numbered elements specifically, because when we were fusing elements by the alpha process, we're adding 2 helium at a time. And they make then lots of magnesium, lots of silicon, things like that. And while they do make iron, while they live and also while they die, so they make some of the iron that we see, they are not actually responsible for most of it. That goes instead to low mass exploding stars, which make the bulk of elements like iron, nickel, and zinc. So we've been talking about these very massive stars. And that's because most low mass stars are not going to do any more fusion, so we don't really care all that much about them. They don't collapse like massive stars do after they are done fusing in their core because they're supported by a special kind of like quantum mechanical pressure. So electrons cannot have the same quantum mechanical configuration as each other. And you can think of this as a parking lot, where every electron needs its own parking space. And when we have lots of spaces or not that many like free electrons floating around, this is not a problem. This is not relevant. But the core has gotten really dense, right? Gravity is still trying to push it together. And so now our electrons are fighting for space. This is like not where you learn to drive anymore, right? It's a high pressure environment. And this pressure is what props the star up against the force of gravity. And that's what happens for most of these stars. But like, what happens if we just like keep adding mass? Eventually, the electrons are going to crash into each other. They are going to start parking on top. We can add some more mass by siphoning it off of a companion, or we can merge two of these stars together. And as you can see, gravity does eventually win here too. Gravity will overwhelm this kind of like fancy quantum mechanical pressure, and the star will just explode. Something like that. And they are really fantastically bright. These supernovae can outshine their entire galaxy. So it's a very big explosion. And we can break it down a little bit and try to get some elements out of it. So we have a carbon-oxygen core, and we can start to fuse that carbon. Things have gotten a little bit hotter since we started adding mass. So the carbon starts to fuse. It'll make things like neon and sodium. But this really is like setting a match to gasoline. The more carbon that we fuse, the hotter things get. And that makes it easier to fuse more carbon. And it makes it easier to fuse whatever carbon is fused into other stuff too. And as this like carbon flame starts to like propagate through the star, we start getting all of these reactions that are feeding each other, making heavier and heavier elements as they go. And we get this big network of reactions that end up going all the way through the star until it completely explodes. Nothing is left behind by these stars. And as they are exploding in this process, these guys make a lot of iron. Again, these are the abundances of elements in the solar system. You can see there's a really big spike there. And a lot of that spike is coming from these low mass stars. So like iron in our blood, or like in knives, I guess, steel knives or something like that, right? Most of that is going to come from stars like these, which is great, but we are still stuck at 37 protons. We have not made anything heavier. So it's nice that we know where they come from, but we still have 81 elements left. But all of these are going to be made in the same way, basically. And by a combination of what's called capture and radioactive decay, which we sort of already talked about. Specifically, the rest of these elements are going to be made by what is called neutron capture. So neutron capture starts with like an unsuspecting, free, floating, loose neutron in a star. And as it floats around, sometimes it's going to get absorbed by a heavier nucleus, usually something like iron. And when that happens, we have made a new isotope. We haven't made a new element yet, but we've added a neutron, so we get a new isotope. But we talked a little earlier, like you can't just add stuff to a nucleus and expect it to all work out. And so most of the time, when you make a nucleus this way, it's going to be unstable and it's going to have to decay. And what ends up happening is that the neutron spontaneously converts to a proton, and the nucleus sheds an electron and what's called an antineutrino, which is great for us because we've added a proton, we've made a new element. And we can sort of just keep doing this, more or less. Just keep adding one neutron at a time, getting one proton out of this deal every single time until we get to 118 protons, sort of. There are two problems with this simple picture. The first is that there's no guarantee that that nucleus is stable either. And the second is that stars don't just have neutrons floating around. neutrons are unstable on their own, so they're almost always bound up in other nuclei. They're not just like out and about during hydrogen fusion. So we need some sort of neutron source. We need a way to generate free neutrons that can be like available and ready to use for this process. And there are two different ways to do this. The first is to have some sort of special fusion reaction that is going to, as a byproduct, produce a lot of free neutrons. Or we can crush protons and electrons so close together that the subatomic particles that make them up rearrange themselves into neutrons. And these are two wildly different options. And so we usually split neutron capture processes into two: a slow neutron capture process and then a rapid neutron capture process. So the slow neutron capture process, or S process, uses this special fusion reaction to get a bunch of free neutrons floating around. And this is a little bit more relaxed. And so it's going to make most of the lighter, heavier elements, if that makes sense. So we're going to start at about strontium. That's the first one we sort of see from this process, which has 38 protons. I don't know. Usually we don't really think about strontium, but sometimes it's in toothpaste, and it's what makes fireworks red. I had to actually look that up today because I didn't know a single use of strontium on Earth. And we'll make things all the way up until about lead and bismuth, which have 82 and 83 protons respectively. So that's pretty good. We're like making progress finally. And the S process is considered slow because the time it takes to actually add this neutron is quite long compared to the time it takes the unstable nucleus to decay, meaning we really can only do this more or less one at a time. Capture a neutron, let it decay. Capture a neutron, let it decay. And we'll sort of get a little bit stuck at those magic numbers. They'll wait a little bit longer, maybe capture some extra neutrons before decaying when they're at like a proton magic number. And that helps us maintain a better balance of protons and neutrons and make some good, heavier, stable elements. And the S process takes place in one of those intermediate late life stages of stars, kind of like the sun. So this is after they have a nice carbon core, but before they have turned into white dwarfs that are hanging out forever. And so at this point in the star's life, we have a carbon and oxygen core, a layer of helium that sometimes lights on fire, honestly, sometimes it burns, and then a layer of hydrogen that also is burning a little bit, but mostly just a ton of non-burning, like cold hydrogen on the outside. And at this stage in a star's life, it is convective, meaning just like hot air rises and cold air sinks, as we all are painfully aware in the summer, the same thing is going to happen in the star. And so the hot material that is in these inner layers is basically going to get scooped up, sort of brought around. And those hydrogen, that cold hydrogen at the top, which is just protons, is going to get brought down. Other stars do this during their life. Like a star being convective is pretty normal, but this stage is unique because usually convection is like confined to its own layer. So the hydrogen in that outer layer will cycle, but it's only cycling with itself. But this one is special because it can like reach down into the core and like actually scoop stuff up. And what we end up with is a weird little bubble of carbon that has been scooped up out of the core. And we are going to just inject protons into our little carbon bubble, right? So the protons that were cold at the top of the star that are falling in are going to go into our carbon bubble. And so now we have a very proton-rich environment, which is the absolute opposite of what we wanted. We are looking for a neutron source. That does not seem helpful, but just like neutron capture can produce a proton capture can produce a neutron. And so that's more or less what ends up happening in our little carbon bubble. I'm going to skip details for brevity, but by capturing a proton, the carbon in that bubble is able to produce a lot of free neutrons, which can then get sort of tacked onto any heavy nucleus that was like already in the star to begin with. So this starts at iron. Just start adding a neutron like every couple of decades. maybe every 100 years, a nucleus will gain a proton and be made into something heavier. And this process is totally fine to make all of these elements in purple. But we start to run into some issues. And once again, we're back to stability issues. So the heavier the element, right, the more neutrons it needs to be stable, which is kind of hard for the S process to do. And also, there are some heavier nuclei that have just no known stable isotopes at all, which this process just cannot handle. It's a complete no-go. And so as the S process is making heavier and heavier elements, it's sticking very close to this nice blue region here. It is not straying far. And so it's sort of limited in what it can make. It can't get to elements like uranium, where you have to cross this big gap of instability. What we need instead is the rapid neutron capture process. Very creatively named because neutrons are captured very rapidly. In this process, the nucleus is going to add multiple neutrons before it decays. So the time it takes to add a neutron is short compared to the time it takes the nucleus to decay. And so every time a neutron is captured, we can think of this as like resetting the decay clock that we have. And so if you can manage to stick one neutron on after the other, you can sort of like outrun the clock for kind of a long time, actually. And we can make really different nuclei this way. And we're going to get helped along once again by our beloved magic numbers, where the S process, so like our process, is sort of going to zigzag along like this, making heavier and heavier elements. And it's going to hang out for a while on those magic neutron numbers. The time to decay is longer there. It's harder to capture. It's harder to capture more neutrons that way. And while they wait there, some of them will decay towards, just like right diagonally, towards this blue area of stability. And so we are going to make those very heavy nuclei like uranium this way. And then we're going to make lots of elements that sort of correspond to decays from these magic numbers. So anything that is like right diagonal from the magic number, we're going to get a lot of that. So that's things like xenon and platinum. And anything that is not on that diagonal, we're going to make very little of. And this is all the stuff that I actually really have never heard of, like rhenium. Sorry, I'm looking at my notes. Rhenium and lutetium are two of the sort of random elements that we can make by this process. And the S process does something similar, but with the proton magic numbers instead of the neutron magic numbers. And so when we look at the abundances, the amount of each heavy element that we have, we see these some little peaks here and here. And there's another one technically over here that's hard to see. And lead, for example, is made by the S process. That corresponds to one of those magic numbers. Xenon corresponds to one of the neutron magic numbers. Yeah. Okay. But to actually capture neutrons this quickly, it's very hard to do. We need like 1 billion times more neutrons per like cubic centimeter than we had in our carbon pocket. That is a lot. And so we're going to rely on very extreme astrophysical events. We're actually not entirely sure where the R process happens. One thing that we are pretty sure about is that it can happen during a neutron star merger. So neutron stars are the dead cores of those massive stars that we like left behind. So this is really just still going. Yeah, the massive stars that we left behind, and they are, sometimes they will be orbiting each other. There'll be 2 of them nearby. And as they orbit, they're going to start to spiral in. And that's what you see in the animation, right? It's like they're going down the drain. And when they collide, we are colliding through things that are basically made of neutrons. That is the perfect neutron-rich environment that we've all been looking for. And so we get the R process where 100 neutron captures can happen every second. And so we can make all of these weird heavy elements, but we need a very extreme environment to do that. And this gets us up to plutonium, which has 94 protons. And the issue is that we're pretty sure, even though we think the R process happens in neutron stars, these merging neutron stars, we're pretty sure that can't be it, but we really actually don't know where else we can get an extreme enough environment to make things like uranium. So we think, basically, in my field, anytime you don't know something, you blame it on magnetism and rotation. So you can say, I don't know how magnets work. I don't. So I'm just gonna have a really magnetic star. Then I'm gonna make it spin very, very fast. Or I'm gonna make a star out of only hydrogen and helium. And it's gonna die as a very energetic supernova and make all sorts of stuff. So there are lots of different theories of other ways to make our process elements, but I mean, they're nice illustrations, but really don't know what they're like. And these are the last stable elements that we can make. Everything else that's grayed out is too radioactive to survive. It doesn't have any stable isotopes, certainly none that could be made by stars. And some of these that are grayed out can be made during the R process, and they just don't live. Like they're made sort of as a byproduct, and they just decay into the other stuff that we actually see. But a lot of them actually are only man-made. They're not naturally occurring, and they're not stable. They can live in a lab for like a couple seconds. So functionally, yeah, we think maybe there are more magic numbers where we can get stable heavier elements, but we haven't found them yet. Well, particle physicists haven't found them yet. I certainly haven't. And that closes out our entire periodic table. That was a very quick tour of the chemical elements. That's great, at least as far as we know. And so you've just been taking this on good faith, that I am telling you something true. I mean, I'm making this up. But the way that we know is by looking at the atmospheres of stars. So stars form out of clouds of gas. They live, they make elements, they die, they put those elements back into the gas, into whatever's left of the gas they formed out of, which can then make new stars. And so when we look at the atmosphere of a star, we're really looking at a historical record. We're looking at the past kinds of events, the supernova, the mergers, that contributed to its chemical makeup before it was even born. So we looked at this graph before. So abundances of the solar system, which are basically abundances of the sun. And you can see evidence of all of these different processes that we talked about. There's a lot of magnesium, there's a lot of silicon from those high mass stars, lots of iron from the low mass ones, and we have all sorts of weird elements like praseodymium over here from the SNR processes. And so a lot of these overlap. They make the same elements in different amounts in different ways, but it's really hard to disentangle any one way of making an element from a star like this. What we need instead are very, very old, very chemically unenriched stars. These are stars that form in the first billion years, half a billion years of the universe. And they're forming out of almost entirely hydrogen and helium. There haven't been previous generations of stars really to enrich them, not very many anyways. And so we can see evidence of sometimes even just one single supernova in stars like these. And what you are seeing here it's the same plot as this basically, where the yellow stars are the abundances in the sun, and the green dots are abundances that we measured from a very old star in a teeny tiny galaxy called Eridanus 4, that we measured some chemical abundances of this star. And you'll notice, compared to this plot, we are missing like a lot of stuff here. There are a lot of blank spaces. It's because, one, there's almost none of these elements in this kind of star. Sometimes there's literally none. And also they're very faint, they're very far away. And so it's just hard to measure. So we end up with these big gaps. But if we look at the pattern, they tell a very different story than the abundances of the sun. So we do see evidence of those exploding massive stars. We get a good amount of things like magnesium. What we don't see are heavy elements. Just like the teensiest bit of strontium, maybe, we couldn't even detect any R process elements at all. This is europium, which we think is made in those neutron star mergers, and we literally detect it. And we also don't see that much of these elements like iron. And what that tells us is that we got some iron from the exploding high mass stars that made this like magnesium and silicon, but didn't get any from the exploding low mass stars. And so means is, since we know the star formed early in the universe, that whatever made this, let's say we didn't know it was massive stars yet, whatever made that had to have happened pretty quickly. There had to be enough time for these elements to be made and returned to the environment before the star formed. And so there wasn't enough time really to make any of these in other stars. And so there has to be some sort of delayed source, something that takes time to make. But because we do know where these are made after doing this sort of thing lots and lots of times with lots and lots of different stars, we can ask questions like, well, we know it's a massive star that's doing all of this. How big was it? Was it 10 times mass of the sun, 50, 100? And how much of every element did it make? That's one of the things we know the least about with respect to where elements come from, is how much of everything gets made by any of these individual events. And so if we can find a star that only has the signature of one single supernova, we can answer that question way better than when we look at something like the sun. And it does beg the question, there's nothing. Why? And when we do this sort of analysis lots and lots of times, we start to build up the story that I just told you about all of these elements that are periodic table. And we start to figure out where they're made. And what I think a lot about is how much of them are made in each of these different events. But yeah, sat through 40 minutes for me to say everything's made in stars, everything that we care about, everything that makes us up during the life or death was made during the life or death of a star. I don't know, I think it's fun. So that's all I have. Thank you.